We'll discuss coherent implementations of climate change and sustainable development policies and ongoing implications for ESG investing. And on March 7th, we'll have Dr. Peter Eichhubel, a senior research scientist here at the Bureau of Economic Geology at UT Austin. And he'll discuss storing hydrogen in the subsurface, challenges and opportunities for low carbon energy. Today, it's our great pleasure to have Dr. Christopher Arges from Penn State, and some background on his presentation. Hydrogen technologies have made substantial progress over the years. Some say that the 2020s will be the decade of hydrogen. And it's not only an important fuel for heavy-duty vehicle transportation, but hydrogen is also vital to decarbonize chemical and materials manufacturing, such as steel and fertilizer production. Proton exchange membrane, PEM, water electrolysis is one of the most efficient routes for generating green hydrogen, and PEM fuel cells then can take the hydrogen and convert it into electrical energy again at efficiencies of over 60%. But a key challenge is the cost from the large amounts of platinum group minerals or metals used in these electrolyzers and fuel cells. 3M's nano-structured thin film NSTF electrodes consist of extended surface electro-catalysts that display some of the highest mass activity values for the oxygen reduction and evolution reactions, resulting in exceptional water electrolyzer and fuel cell performance while using less platinum metal. That would reduce the cost. However, the mesoscale geometry of the organic crystalline whisker supports used in NSTF have not been systematically tuned to examine how extended surface area structures affect electrochemical reactivity. So Dr. Arges will describe his recent work to investigate a new class of extended surface area electrocatalysts generated from self-assembled block copolymer templates, where he systematically tuned the mesoscale morphology through control of the self-assembly process, where the morphology was shown to affect kinetics. The second part, he'll discuss some recent work investigating electrode binders for high temperature PEM electrochemical hydrogen pumps, a technology that purifies and compresses hydrogen from gas mixtures. We'll also talk about experimental framework to de-convolute various kinetic and transport related resistances that arise from binder chemistry and selection for HT-PEM electrodes. And he'll conclude with an outlook of electrochemical hydrogen pump technology for storing and distributing hydrogen in the natural gas pipeline infrastructure to alleviate or reduce hydrogen transportation costs. And so we really appreciate you being here, coming here. Let me give you some background of our speaker. Dr. Chris Arges is an associate professor in the Department of Chemical Engineering at Penn State. His research interests are at the intersection of polymer science and electrochemical engineering. As an Illinois native, he earned his BS in chemical engineering at the University of Illinois at Urbana-Champaign and a PhD in chemical engineering at the Illinois Institute of Technology. He was a postdoc scholar at the Pritzker School of Molecular Engineering at the University of Chicago. And he's also the recipient of the NSF Career Award, the Electrochemical Society Toyota Young Investigator Fellowship, and the 3M Non-Tenure Faculty Award. So we are so glad to have you here, and thank you for your time. We'll have Q&A session after the presentation, and please, if you're online, use the Q&A function and not chat. Meanwhile, let me pass you the microphone.
Thank you. Can you all hear me? All right, great. Let's try to get this.
You may have.
Okay. All right. Good afternoon. Thank you for the wonderful introduction. I'm happy to be here at University of Texas, Austin, place I have tremendous admiration for. It's really a leader of so many different areas: energy, electrochemistry, separations, materials, nanotech. So it's been a wonderful visit. This should work, hopefully. This is this one. So I just want to tell you a little bit about what our research group does. And we both do fundamental materials research. In particular, we like to work with self-assembled block copolymers and control their nanostructure and try to understand how the mesoscale morphology may impact things like reaction kinetics, transport phenomena, and electrochemical materials that are actually used in devices. But sometimes, like these block copolymer templates, whether they're electro-catalysts or nano-structured polymer electrolytes, they can't be used in practice for a host of reasons. They may be unstable, the reactivity might not be good enough, but control through the mesostructure would give us fundamental information, and we can leverage this information for the design of new materials. So I'll be talking a little bit about this work from this paper in small later today. And then my group also works with translational materials, what I like to call translational materials. And what I mean by that are materials we actually use in devices, materials that we can actually share with industrial partners where they can test to see, hey, are these promising materials for actual applications? So what you're sort of seeing here right now is this is a porous ion conducting material. Those are ion exchange resin particles that would normally be sand-like. They're immobilized with a polymer binder. So we can hold this in our hand. And then here, it's a little hard with the camera, but this is a high temperature polymer electrolyte membrane electrode assembly. So we have electrodes on the membrane. This is work we've done in bipolar membrane. So part of my visit here this early part of the week in Austin is to go visit my former student who works at EnergyX, and they're interested in materials like this for lithium recovery from brines. So the other thing you'll see today is not only do we go into the lab, we do fundamental material studies, we make translational materials for partners, but we also perform device level studies, right? And we're really interested in connecting the material properties to the device performance. So one core area of my research group is in the area of ionic separations and in the context of critical mineral separation. So what you're looking at here is a membrane capacitive deionization cell. And this is where we use two porous electrodes. We can electrically bias them and we can pull ions out of a liquid stream. But in this context, we were looking at copper ion removal. So this copper is diluted with a brine solution and collecting it on an electrode with this bipolar membrane. So this bipolar membrane is useful because we can do in situ pH adjustment while we're taking the ions out of solution. And so my student, Tammy Kokanari, who's a PhD candidate with my group, this is a work that he's doing. And you can see here, he's pulled out copper at a much greater rate than sodium. And then by creating this acid environment in the bipolar membrane, when we plate the copper, we get its metallic form and not a metal oxide. That metal oxide can be problematic because it can passivate the electrode. And when you get the metal oxide, you sort of get this bluish color copper oxide, but when you get the metallic copper, you get the copper that we know in copper wiring and copper piping. And this is sort of informed by Pore diagram principles, right? The thermodynamics, the electrode potential and pH that we can, exploit to achieve selective separations. So I want to talk about the people who did the work before I really jump into it today. The work has been done by primarily, you'll see today, by two PhD candidates in my group, Deepa Bhattacharya, Kartik Runagiri. And there's also a lot of work done by a former PhD student of mine, Gokul Venugopalan. And these various funding organizations have supported our work in the high temperature PEM area. I'm also, an entrepreneur. I'm a co-founder of Ionomer Solutions LLC. Part of my conflict management plan is to disclose this. So the materials you'll see later in the second part of my talk are commercially available. All right, so I want to tell you about hydrogen at scale and the importance of reducing platinum group metal loadings in those technologies, really for them to grow and proliferate. And then I'll tell you about a new class of extended surface electrocatalysts with low platinum group metal loadings. So this is borrowing ideas from block copolymer nanoscale lithography to get nano-structured electrodes that have, I would argue maybe competitive state-of-the-art data. Then I'll transition to a new area in my group where we're looking at putting hydrogen in a natural gas pipeline to reduce the cost for hydrogen transportation. And one of the things to do that, we need to use an electrochemical hydrogen pump to purify the hydrogen that's stored in the natural gas pipeline. So I'll tell you why can't we put 100% hydrogen in the pipeline? We have to dilute it, or tend to dilute it with the natural gas, but we don't want to burn the hydrogen. We might want to use it for something more useful, like fertilizer production, using it as a reducing agent for steel manufacturing, or hydrogenation reactions. So hydrogen at scale. So this is from Brian Pivovar at the National Renewable Energy Lab. He's the director of H2New. And I think hydrogen was largely touted for powering electric vehicles through fuel cells, but it really has a much broader role than that. And so I'm not going to go through all these different bubbles here, but I want to point out two things. That hydrogen, we can use green hydrogen as part of a feedstock to make fertilizers, ammonia production. And I said already about using it as a reducing agent for steel manufacturing. And when we look at the total energy consumption in the US, the largest fraction of energy consumption comes from an industry. And so I want you to think about hydrogen in a broader term, that it's really central decarbonizing industry, which is the largest greenhouse gas emitter and consumer of energy. So if we just look at fertilizer production today at steel manufacturing, 10% of CO2 emissions in the United States come from just making those two things. But we cannot live in a future without steel and fertilizer. So if we're going to try to achieve, 50% greenhouse gas emissions, or 50% reduction in greenhouse gas emissions by 2030, we have to decarbonize industry and net zero by 2050, and we need to do it now. Hydrogen production can be achieved through PEM electrolysis. So these blue blocks here are proton exchange membranes. We feed in water, we put electricity in, we get hydrogen and oxygen out, right? We could also use this hydrogen. We could store it in a natural gas pipeline. We could store it in tanks, and we could use it later on to meet electricity demand. So as many of you probably know, solar and wind, they're intermittent energy sources. Sometimes we need energy storage technologies to provide power. If it's a hot day or the sun's not shining, the wind dials down. And hydrogen is also sort of seen as like a seasonal energy storage or long-term energy storage technology. But in the fuel cell case, fuel cells are very mature. There's been a lot of progress. The ultimate goal by Department of Energy is to get this loading per kilowatt net power in a fuel cell stack. That's really the equivalent amount of platinum you find in your catalytic converter in your vehicle today, right? So that's sort of the goal. And if we look at platinum nanoparticles decorated on high surface area carbon supports, you would need to achieve a 3x, 6x reduction. So that's not too bad. Not easy, but not too bad. If we look at the water electrolysis case, and this is really the big growth area, quite frankly, this is a little bit more challenging. We don't use platinum in the anode where we do water oxidation, and we use iridium oxide. That's the state-of-the-art catalyst. We get iridium from mining platinum, and iridium is also used in a lot of defense and communication technology. So it's not like we can just allocate all the finite resources of iridium for hydrogen production. So this was a nice paper by Tom Yaramillo and his students saying, if we at this current large loading of the iridium in the PEM water electrolysis, and if we were to allocate 10% of the iridium that we mine every year to PEM electrolysis at this loading, and we knew the anticipated hydrogen demand, it would take 200 years to build out PEM electrolysis, and we need to decarbonize now, right? So this is not possible. We need to really achieve a 10x reduction in iridium oxide. And so, the playbook largely has been, we just need some fancy new nanoparticles, like we have a core particle and then like a monolayer of platinum coated on it. And we would get to these ultra low loadings, and this would solve all our problems. So our commercial catalysts, we tend to have these platinum nanoparticles and fuel cell catalysts decorated on high surface area carbon. That's here. We can do a rotating disc electrode experiment in the lab. That's these dark lines or the gray lines, and they give you the mass activity. That's how much current we get at a certain voltage. We want very high mass activities. So the gray lines are what we do in a very idealized system to get the mass activities. And we're really good at controlling nanoparticles. We can make all sorts of different things, or not me, but people like Professor Portal and others, they can do all sorts of fancy things with nanoparticles. But then control at the mesoscale in the porous electrode, that hasn't been mastered as well. And then, so just to give you an idea of what these nanoparticles sort of look like, this is sort of this porous, octahedron shown here. But then if you were to put it in an MEA, an actual device, our mass activity in idealized case is great, but in the device, not so great. There are all these fancy new catalysts that look great in model experimental conditions, but haven't been tested in devices. So what we want to do is demonstrate excellent performance both in the experimental condition, but actually in devices. So one platform that sort of does this that's out there is technology by 3M Corporation in Minnesota. And this was work developed by Mark Debbie. And what he does is takes this parylene, and he grows organic crystallines from this material. And he makes these very, very, very high surface area supports shown here. And then he uses top-down deposition, so you can sputter metals on top of these supports to get these really, really high surface areas. You could do several different types of metals. You might put down, like in this case, a layer of tantalum followed by a layer of platinum. You could co-sputter different metals together. So if you alloy with cobalt and nickel, you can get higher mass activities, but sometimes like cobalt and nickel have degradation concerns. And then if we were to look at, a fundamental equation, like this is the kinetic current at a given potential, we want to get as much current density as possible at, say, 0.9 volts. And I don't want you to look at all of the parameters in this equation, but I want you to see this A, which corresponds to the surface area. And this is the amount of surface area per geometric area. So 3M's nano-structured thin film technology, they get 8 centimeters squared of area with these extended surface supports per geometric square centimeter. So if they were to do this rotating disk electrode experiment in the lab and compare, this is sort of the mass activity, they'll get anywhere from, around 0.3 to up to 0.9 milliamps or amps per milligram of platinum. This is with an alloy, so they've alloyed with nickel in here. And then, so this is competitive. It's not as good as some of those other data points that I showed you in the previous slide, those gray bars. But when you actually put it in a device, they do satisfy the Department of Energy fuel cell targets, right? So the current target is this 0.125. They've been able to get 0.086 grams of platinum per kilowatt of energy. We want to get, eventually you get to a lower value, but this is excellent performance, right? So this high surface area support is really useful for promoting electro reactivity at low platinum group metal loadings. If we look at the water electrolysis case, the metrics is, okay, well, what current density can you get? I think at 1.8 volts per platinum group metal loading. So they were able to get 5 amps per square centimeter at this loading, 0.36 milligrams of platinum group metal loading. That would be both the platinum and iridium and the MEA. And this exceeds that 4 amps per centimeter squared at 0.5 milligram of PGM loading. So very, very, very promising platform. And then furthermore, what's really important, you could get electrodes, right, that are very reactive and low PGM loadings, and you get this fantastic data, these polarization curves I'm showing. But if they don't last thousands of hours, they're no good, right? The economics don't make sense. So one of the nice things, we'll talk a little bit about durability later on, is that these sputtered electrodes give rise to good stability. And that is particularly challenging at low loadings. So now I want to tell you about our work in this area, what we think could be, new breakthrough material to compete with 3M and NSTF, potentially. I don't know. So I come from the world of block copolymer self-assembly, and block copolymers are a versatile nano-structuring platform, right? If we think of a canonical AB diblock copolymer, A and B, one block's oil-like, one block's water-like. Oil and water doesn't mix. And if you try mixing it, they would phase separate. But when you tether them at one point, right, they'll phase separate, but at the nanoscale. And you can control the type of nanostructure you get by how long one chain is to another. We call that the volume fraction up here. And so if they're equal, you get like a sandwich-like structure, like these lines called lamellae. If the red is more longer than the blue, you would get blue cylinders in a red C. And conversely, if blue is longer than red, you get red cylinders in blue C. And then the size of your periodic structures are dictated by how long the chain is, the degree of polymerization, right? there's another industry that currently uses this for a different technology, and that is semiconductor manufacturing, or it's an emerging technology in semiconductor manufacturing. So this was in CNE News a few years ago, patterning with polymers. When you do lithographic patterning, the smaller and smaller the feature size, especially at high density. This is difficult with conventional top-down optical lithography, and so we might go through this bottom-up lithographic patterning through self-assembled block copolymers. And so all these companies I'm showing here either have a current R&D program or had a current R&D program at one time in controlling the self-assembly of these block copolymers to make FinFETs. These are transistors or bit pattern media for data storage. And so the thing is, this in some ways, this is not the most mature technology, but it's been established for a while. But you can get sub 10 nanometer features with long range order. And I forgot to say, those structures I showed you by 3M before, those crystalline structures have diameters of 50 nanometers, right? So not sub 10, but they're very long. They're about 1 to 2 microns long. But you can get high aspect ratio structures when you transfer the block copolymer into substrates. So we've done this. We've actually made electrocatalysts for the first time from this self-assembled block copolymer template. But we don't do incipient wetness impregnation. We try not to put the catalyst in the block. What we're going to do here is do this self-assembly process, create these nanoscale patterns, these extended surface area supports, and then put a very thin layer of catalyst on top. And that's what I want to tell you about. We wanted to measure the electrochemical reactivity, so we had to learn how to do this process on glassy carbon tips. This is what the substrate that we use in that experimental setup. We graphed a non-preferential layer that makes sure both block copolymers will sit perpendicular to the surface. We'll put this block copolymer on top. We'll spin coat it. We anneal it. We've used a very simple one, polystyrene methyl methacrylate. Then I'll show you later on. In this methyl methacrylate, we grow an aluminum structure that will serve as our hard mask support. And then we use a reactive ion etcher. These are all tools you find in a nanofab in a clean room, right? We'll etch away the polystyrene block and we'll be left with the aluminum oxide extended surface. And then we go ahead and we sputter the electrode on top. So I want to tell you a little bit more about the sequential infiltration synthesis using atomic layer deposition tool. This is where we grow the aluminum oxide in one of the polymer blocks. So we pass in trimethyl aluminum. This will coordinate with this ester group, this carbonyl group in the methyl methacrylate block. Then we'll purge the chamber, but that trimethyl aluminum will hang around. We pass water and we make aluminum, and we'll do this multiple times. And the number of cycles we do in this process will dictate the width of this alumina structure within the block copolymer. So the SEM images that you're looking at right here, this is after we've etched away the polystyrene with oxygen plasma. And these are perpendicular cylinders, right? And these are lamellae structures, right? So again, we're using that block copolymer template to control the mesoscale morphology. And then we can use another handle to control the support width through the SIS process. So this is our block copolymer template. This is our alumina structure on the glassy carbon after growing the alumina and then etching away the polystyrene. And then this is after we coat a very, very thin layer of platinum on the surface. So we have our extended surface electrocatalyst now. So one of the things my student Deepa wanted to find out, how low can we go? And we really wanted to get to the lowest loading possible, like 1 or 2 nanometers, but I think that was a little over optimistic. So we went ahead and put down 2 nanometers here, and this gives you, we used ICP, or we did microwave digestion followed by ICP OES to quantify the loading. I mean, these are very low loadings, micrograms per square centimeter of platinum. And if we did this cross-sectional STEM EDX imaging here, so here's our block copolymer, our structure. This is actually the final structure. And we can image the elements. So we see the aluminum, but we just see here the platinum at the surface. We don't see it coating the sidewall, okay? Then we went ahead and put down 4 nanometers of platinum. So we're over here now. So we're at a higher loading. I mean, from top down view, I mean, more or less these images look the same. Okay, so that's why you have to do these cross-sectional imaging to look at this. We start to see the platinum coat the sidewall. And then we did, 6 nanometers, right? But what we found in that rotating disc electrode, and I know this is a lot of data here, that 4 nanometers, which gave us 5.8 micrograms per square centimeter this year, was the right balance, right? We got enough sidewall coating where that platinum could make connection with the glassy carbon tip underneath, but it wasn't too much that the platinum underneath was being wasted, right? We just wanted on the surface to participate in that oxygen reduction reaction. So that's sort of what we did for all the different mesoscale morphologies that I'll be showing later on. We sort of stuck to 4 nanometers of platinum, but this is something we're still optimizing in my group. So in this next part, I want to tell you a little bit about, does that mesoscale morphology, something, 3M does not control with those organic crystalline materials, can that affect the kinetics? And how does it affect the kinetics and or mass transfer? So that's what I want to tell you about. So this is a linear sweep voltammogram ran in my lab with a rotating disc electrode setup. And we analyze the current density we get at 0.9 volts. We then will normalize that to the platinum loading. And we looked at several different morphologies. So the C here stands for this one. This first one is perpendicular cylinder. This is perforated structure. So we have like a perforated structure where we have holes and we put platinum. And then we have these lamella structures with different line widths. And what I want to point you to first in this lamella structure, these are the degree of polymerizations. This is the molecular weight of the Copolymer. So this is a higher molecular weight. This might be something like 40 some nanometers. This might be here like 20 nanometers. When we're making the width smaller, we're getting higher mass activities, right? So that would say higher surface area, better performance. In the cylinder cases, these are our standing cylinders, and this here are our perforated structures, right? So this is where we're taking advantage of that block copolymer lithography. We put down the platinum here that these extended surface supports, they gave the highest mass activity. We measure the electrochemical surface area using cyclical photometry, measuring the hydrogen underpotential. I won't go into the details of that. But what we're seeing here is that this morphology, right, has a profound impact. Control of the morphology at the mesoscale has a profound impact on electrocatalytic activity, right? And I showed you earlier on that even when you make fancy nanoparticles, if you can't really control the mesoscale morphology, it can be difficult to infer how that nanoparticle structure is affecting electrode performance. So there's a lot more here that I'm not going to go into too great detail, but we were curious to know, maybe with the mesoscale morphology, we could affect like the fusion of oxygen through the structure. And how would we know that, right? And we can use the Kotechi-Levitch equation. So in this rotating disc electrode, you have that glassy carbon tip on the shaft. You can rotate the shaft real quick. And as you spin the shaft faster and faster, you'll get higher and higher limiting current densities. And this measured current we're getting, 1 over the current, is equal to a contribution from the kinetic current and the diffusion current. And we can do this analysis to estimate this Levitch constant. I'm going to spare the long equation here, but this Levitch constant is proportional to the diffusivity of the reactant to the 2/3 power. But for all the different morphologies I showed you, we did not really see a difference in the Levitch constant and the diffusivity. In the case of surface area, we see the electrochemically active surface area. We see that this extended surface, because it had a very, very high surface area compared to the other ones, this is the reason why we got the highest mass activity. And this is important, right? Because I did not use the most challenging block copolymer. That periodicity is 15 nanometer lateral feature size. We can go sub 10, okay? We can do 6, 8 nanometers. So a lot of area to improve, but proof of concept demonstrated. The final thing I'll tell you about in this part is durability. Durability is important, right? So you cannot just go into the lab, make new functional materials and get great things, and if they fall apart, they're not useful to anybody, right? And in the world of fuel cells, the shift now is more towards heavy-duty vehicle applications because we've gotten very good at batteries, and you probably see a lot of Teslas driving around town, at least I do. But fuel cells trying to make be a competitor to battery electric vehicles, that's a little bit of a challenge. I think there's some niche applications. Now in heavy duty vehicle transport, where this vehicle needs to be on the road all the time, like a truck, marine shipping vehicle, aviation, fuel cells are actually very good, right? You can refuel fast. They have higher energy density values at when you need a large amount of power. But when you have a vehicle that's transporting goods all the time, it needs to be stable for a lot longer than a light duty vehicle. And so one of DOE's targets is to get, system lifetimes of 25,000 to 3,000. Fuel cell here, I think we've already offered 6,000 hours stability, so we're sort of here, but going to 25,000 hours stability is a challenge. And so that state-of-the-art catalyst is those platinum nanoparticles on high surface area supports. And if you run an accelerated durability protocol, that's a way of how we determine how stable the materials are. We'll see for this platinum on carbon that these platinum nanoparticles, you'll have oxidation of the metal, you'll get metal ions, you'll have particles coalescing or aggregating together. And then as such, when you lose platinum from the system or the particles get bigger or they're touching each other, you don't have that exposed surface. We see this linear sweep voltammetry sort of shift to the left. And then we can measure this mass activity loss over time. So this is a paper from Georgia Tech looking at that at 20,000 cycles. And so we ran a very identical or similar, I believe, same up to same potential. We started from 0.05 to 1 volt, but same number of cycles, same conditions. We only saw 11% loss in our mass activity, not over 50%. And then our structure before and after, more or less the same. So we were very happy. We were impressed with this data. And so there's a lot of room to go. So this sort of wraps up part 1 of the talk. You can use this block copolymer self-assembled templates to make extended surface area electrocatalysts. You can borrow these ideas from integrated circuit manufacturing. Not only do we have really good performing materials, we think, but you could do some fundamental studies to understand how the mesoscale structure impacts kinetics and transport. But we think we can do better, right? We could alloy, we could get better sidewall coatings at low loadings, maybe using atomic layer deposition. And if you were to make a 100 nanometer tall structure at the same width, sub 20 nanometers, you can get to 18 centimeters squared per geometric area. 3M was 8 centimeters squared. So we think this is possible, but yet to be done. And there's just a rich design space to explore. So we're thinking at how do we change the alumina support to something electrically conductive? Can we do metal alloys, deposition method? Can we put these on membranes? Those are things we're all working on, and I'm not going to tell you about today. So next part of my talk is on hydrogen pumps, but I needed to tell you first why storing and distributing hydrogen in natural gas pipeline is important. So wow, breath. Hydrogen, right, was the first Earth shot by DOE, right? Because it's important for decarbonizing heavy duty vehicle transportation industry. And what we want is low cost green hydrogen. And so the current cost by electrolysis is, more or less $5 per kilogram, but we want to go to $1 per kilogram in a decade. But there are other costs that are not factored in here. And that's the delivery and dispensing costs of hydrogen, which are quite high. And this could, be a wrench in the gears. So currently most hydrogen today is delivered through trucking, right? So most of those trucks are running on fossil fuels. So, this is an issue where we want to address is this delivery cost of hydrogen. And there's an idea, can we leverage existing infrastructure in the United States to do that? And the natural gas pipeline is one of those ideas. There is a program within Department of Energy called HyBlend. And the idea is that you could have centralized production facilities potentially of hydrogen, and you could blend it into the natural gas pipeline with natural gas. And then a lot of times you could just burn it with the natural gas, right? But expensive electrolytically produced hydrogen to burn it is maybe not such a good idea. But if you're doing chemical manufacturing, you really need high purity hydrogen. And so what we want to do is purify that hydrogen at the endpoint use. And I want to tell you about a technology called electrochemical hydrogen pump, where we oxidize this hydrogen, send the electrons around. So we break down this hydrogen into protons and electrons. We have a membrane that'll take the protons, block all the other gas components from coming across, and we recombine the protons and the electrons to make hydrogen. And there's, analysis, PEA analysis of what are the potential savings? So if you're moving a lot of hydrogen per day, it's not a panacea everywhere in the country. So like in New England where, natural gas pipeline is expensive, your cost for hydrogen delivery costs only reduce so much, but like, here in like the Gulf region, it's like super cheap, or the Great Plains, you can deliver hydrogen at really, really low costs that are enticing. But there's one thing to consider. You cannot put pure hydrogen in the natural gas pipeline because hydrogen is very reactive and the pipeline was not built to deliver hydrogen, and it can embrittle the materials. So this hydrogen pump, I've already explained this. You have, again, hydrogen oxidation, electrons, protons come around, recombine it. You have to expend electricity. I like that it's called a pump, but even though there's no moving parts. And 90% of commoditized hydrogen in the US comes from steam or methane. But this membrane is really selective. All the other gaseous components wouldn't permeate across, and so you get really high purity hydrogen on the other side. And so what we're really interested in eventually, I won't show you this today, but we're interested in purifying this hydrogen from natural gas mixtures. But I will be showing you how we've taken hydrogen from reformed hydrocarbons, heavy CO mixtures, and gotten high purity hydrogen. But like, if you're cracking ethane to make ethylene for plastics and so forth, you might want to recover that hydrogen for use later on. And this pump can do it. It's a competitor to pressure swing absorption. So there are, a few works in this area. Some of them involve like high temperature ceramic materials, right? 500 degrees C. Most of the literature reports in this area use just methane with hydrogen, and they don't actually use what's in the natural gas, which is like alkanes, dihydrogen sulfide. These are contaminants that will poison your electrocatalysts, right? This is unpublished data by BASF from a workshop I participated. So they actually do put some impurities in there, but they won't tell you. But they, were purifying hydrogen from a methane mixture, impurities, and did this for 10,000 hours, right? But what are the requirements for this technology? The gas mixtures we're putting in the gas pipeline don't have a lot of water content. So normally the membranes for these fuel cells or electrolysis have water with them, and that water is really important for mediating ionic conduction within the membrane. So we need an anhydrous conductor, okay? We need things to tolerate impurities, but most work in this area, if you're going to HT-PEM, have looked at how do you purify hydrogen from reformed hydrocarbons with CO. What happens when it's dihydrogen sulfide at 5%? You need to get high purity hydrogen and high recovery. This will be important later on. The nice thing in this pump, not only can you separate the components, but you can compress the hydrogen gas, right? And you need to be energy efficient. You do not want to exceed the lower heating value of hydrogen. So I want to tell you about our work in this area. So we are, even though I gave a first half talk on catalysis, electrocatalysis, I'm not a catalysis person. But I want to tell you now about another important component in the electrodes, and that is this electrode binder. So I probably come from the world of these polymer electrolyte membranes, ion exchange membranes, however you want to call it. But we have a very good membrane for this system. But in the cell, so we have our membrane, we have our anode, we have our cathode. The anode, we say is this graphitic carbon that's electron conducting, decorated with platinum nanoparticles, and this is sand-like, right? But we need to process this into a freestanding porous electrode, or an electrode that's appended to a membrane or a gas diffusion layer. And to hold those particles together, you need an adhesive, like a glue. And that adhesive, a glue, oftentimes in the low temperature case, is the same chemistry as this membrane. And it will coat the surface like this, right? And this coating on the surface will have a real impact to the electrochemical reactivity of the particles. And really, much is unknown about how this binder affects cell performance. How does it affect conductivity under thin film confinement? How does it affect electrokinetics and gas transport? And to illustrate this point a little bit further, I took my same membrane, same catalyst type, same catalyst loading, same cell temperature, same flow rate, same conditions, and I changed the glue from this acid and bid polycation to this phosphonic acid ionomer. So this acid now, this phosphoric acid here, the phosphonic acid has been put on the polymer. This has no liquid acid. So this NEA1, these are the open data points for different temperatures. And if we try to get high current, that's the rate at which we're purifying hydrogen at the pump. As I try to get the current higher, move more hydrogen through the pump, my voltage skyrockets, right? I'm using all this energy and I'm not getting any more hydrogen purification. But if I change that adhesive to a different material, hey, right, I'm getting a lot more current now at lower voltages. And why is that the case? This binder has a really big impact on hydrogen pump polarization. So I'm gonna, I think in the interest of time, skip over this really fast. We have a very good membrane, conducts under wide temperature. We sell this commercially, stable for conditions. And furthermore, it hits Department of Energy's heavy duty vehicle truck applications in terms of the area specific resistance, that's the thickness of the membrane over conductivity. You don't want just high conductivity. This is what you want. And you know, at high temperatures, we can get under 20 milliohms/centimeter squared. And then the hydrogen crossover is really low. It's about 2 milliamps per centimeter squared. So you can back calculate that into a hydrogen crossover. And that's important in the heavy duty vehicle area because the fuel cell cost, the fuel cost for the heavy duty transportation is 3 times higher than the capital cost of the fuel cell stack. So I want you to think about the membrane and binder chemistry a little bit. And this membrane, you want low gas crossover, it needs to be mechanically robust. You don't want to short the cell. You don't want electron, you want it to be electron insulating, but you want both the membrane and the adhesive to be highly conductive, chemically stable, no excessive swelling. And then this binder, this adhesive in there, you actually want high gas permeability, which is different from the membrane. You don't need mechanical integrity necessary. You just need it to hold the electrode particles together. And then you want to be able to process these electrodes with, you know, non-toxic solvents technically. You don't want the chemistry in these binders to interact with the electrocatalyst surface. And you actually need to move electrons around in the electrode. So actually then to be electrically conductive is a bonus. And so this is, you know, a paper by General Motors talking about the importance of these binders. And if you could get a binder, right, that had less anions to absorb to the surface and, you know, was like Swiss cheese where it allowed the gas to go through, that would be advantageous. You know, so how can we measure these properties for these thin film materials and electrodes? And can we do it without having to make an MEA every time or going to the rotating disc electrode where there's liquid supporting electrolyte in there that will, you know, obfuscate the parameters that we're really interested under the conditions we're interested, which is with no liquid. So my student Deepa again, he made these interdigitated electrodes using optical lithography. And here we used incipient wetness impregnation to decorate using the block polymer template to put this electrocatalyst on the electrode surface. So once we put this block polymer in there, we put these metallochlorates, they exchange into one block. We then use reactive ion etching to reduce the metal. And then in some cases, we get iridium oxide. If we're doing water electrolysis, this is fine. If we get the oxygen reduction, we get platinum oxide. We reduce the platinum oxide to platinum with argon plasma. And so we put this thin film of nanocatalysts on this interdigitated electrode. So I'm going to skip over this, but this just shows here our top block polymer, you know, transferred into electrocatalysts with different morphologies on these interdigitated electrodes. We can monitor the evolution of this chemical structure with XPS. Nobody had done this before. We were like worried, will this work? So here's our platinum interdigitated electrode, and we put 2 bolts on it, and we get some water electrolysis as indicative by this hydrogen and oxygen gas. But if we put iridium oxide nanowires on this platinum current collector, which is a good water oxidation catalyst, so like, you know, with no volts applied to these little circuits with this perchloric acid droplet on it, they look identical, right? You can't see the nanoscale catalyst. But with those iridium oxide nanowire catalysts, boom, a lot of hydrogen and oxygen occurring, and that's sort of what you see here in this linear sweep voltammogram. But we're interested in thin film polymer electrolytes, so we remove this liquid droplet and we coat it with a very thin layer of that ionomer material, that adhesive that is used in the porous electrode. And we can put different catalysts, and we see differences in reactivity observed depending on the platinum group metal type. So for the high temperature systems, we ran a hydrogen pump as opposed to water electrolysis. So we feed hydrogen into this chamber with our interdigitated electrode, decorate nanoscale electrocatalyst. And here's our 2 binders shown before. The y-axis is up here, 8 milliamps per centimeter squared. This is 2.5. So with that acid here, it's not too surprising the acid absorbs to the catalyst surface. It can block gas transport. We see we have a lot more polarization. We get lower limiting current densities. Here with the phosphonic acid ionomer, we get less polarization and higher limiting current. And we've taken all that data we collect in the lab, and we can fit that to our current distribution model or voltage loss breakdown model, and deconvolute the contributions in these curves from reaction kinetics, ohmic losses, and mass transfer. And what I want to tell you here is that, okay, like in permeability, we can look at the limiting current in the MEA, the actual cell, versus what's on the IDB. And the data that we get on those little circuits, right? There's only a 2 to 4 factor difference between what we measure on the little interdigitated electrode within the MEA with different materials as a function of temperature. If we look at the exchange current density, which is sort of a proxy for the reaction rate coefficient, we're within a factor of 5 to 10. So it's not perfect for this model system, but what our argument is that this can be used as a high throughput, cost-effective platform to, down select, promising new binder materials. We use 100 times less platinum group metal. We don't need a membrane, and we don't need cell testing hardware. All right, so I want to tell you about purifying hydrogen from CO gas streams, and we're going to use our best binder. We have another binder I'll tell you about quickly again. At that time, last year, this was our best binder in our membrane. And we can feed in syngas, which has 40% CO in our gas stream with 25% hydrogen. And we can feed in other gas streams that are reformed hydrocarbons with lower CO content. And what was great about this system, because we can go to higher temperature, that the higher temperature, this ion pair, the acid doesn't evaporate from there. We don't have acid in the electrodes. We can operate at higher temperature. And then as we operate at higher temperature, we can pull more current, which is the rate at which we're purifying hydrogen from the hydrogen pump. And nobody had done this with large CO contents over 3% before. And we did it at 40%. So what was sort of interesting that we said, okay, the higher temperature, the platinum can tolerate this carbon monoxide, which is this catalyst poison, better. So if we look at the carbon monoxide content in different gas feeds at different temperatures, we see here at 220, it didn't matter if we had 40% in a gas feed or 20 ppm. So it seemed, that idea, that hypothesis, right, that higher temperature is paramount to tolerating large CO content. But then if we look at the hydrogen content, we saw here that our polarization was also a function of how much hydrogen was in the gas feed. So we actually wanted to know, to look at this a little bit in further detail. And we did this current distribution model again. And I had talked to people who do DFT simulations, and they didn't think CO absorption on platinum would change all that much with 60 degrees. And we tried to back out the absorption coverage of CO on the electrocatalyst with this model, and we didn't see it change a whole lot with temperature. It was more of a function of the CO content in the gas stream. But if we look at the exchange current, right, how fast we're doing the HER kinetics, that was a strong function of temperature. So what this tells me is actually we do have an electrocatalyst that's CO tolerant, we would do better. So this is sort of an active area that we're still trying to work with a little bit, of like trying to understand what happens when you go to high temperature, different catalyst materials. Is it the contaminant poisoning of the catalyst, or is it improved kinetics for the reaction you're trying to do? The system is stable for over 100 hours for purifying hydrogen from syngas. So I won't elaborate on that. I want to say here, if we look at a conventional process, normally how you deal with the CO, you can make further hydrogen through a water gas shift reactor after reforming methane. And then you use pressure swing absorption to make pure hydrogen, and then you'll compress it. But this hydrogen pump, like you could take this heavy CO mixture from a methane reformer, purify the hydrogen and you can pressurize the hydrogen at the same time. So you can simplify the process with this technology. And then one of the things the reviewer asked for this paper is, what was our hydrogen recovery from the cell? That's really important for the economics and the purity. But we think we can do better on the purity with thicker membranes and further optimization. So 3 more slides. There's a new class of binder materials where they take this phosphonic acid ionomer and mix it with your traditional low temperature system. Nafion, this is a fuel cell system. This is from Los Alamos, where they said, okay, we mix these two, right? We get higher conductivity in the electrodes. And when we get higher conductivity in the electrodes, we get higher power density, right? So the black line is we just have Nafion. The red line here is we just have the phosphonic acid ionomer. And if we mix the two, we get higher. And this is at 160 C. And then if we mix these two and we look at different temperatures, 80, 120, and 200 degrees C, they were able to get 2 watts per centimeter squared. And this was a record in HT-PEM fuel cell performance. And this was really attributed to higher ionic conductivity. But we think this is not just ionic conductivity. We think this is also due to reaction kinetics and gas transport in the electrode layers. So my other student, Kartik, is studying this. And we looked at a different perfluorosulfonic acid material that's analogous to naphthalene called equibion. And we can take this PTFS-PA, this phosphonic acid, and mix these two. And when we add the equibion, this conductivity here jumps up here. So you do get higher conductivity to equibion. This is on a thin film, which I showed earlier. But this one we have to make in the lab. Like we have to polymerize the monomers, and we have to functionalize it. Could we take a commercial material off the shelf and get the same thing? And we do, we see it, right? If we take polyvinyl phosphonic acid, we add equibion, we see the conductivity jump up, but the conductivity is not as good. So we made an MEA. We tested the fuel cell performance. So here, the red lines, right? This is that PDPA that's really bad, right? We try to pull current and the voltage just skyrockets. It's no good. We add a little equibion to this commercial polyvinyl phosphonic acid. We see, okay, yeah, we can pull a lot more current. We can then get to some current. This here is our phosphonated ionomer by itself, but then when we add equibion, we could go up to 5 amps per centimeter squared. That was exciting. So this performance was enhanced with equibion to the cell. But what I want to tell you is how they impact reaction kinetics and gas transport. So these are Nyquist plots where we looked at the MEA. And the thing is, when we add equibion to the phosphonated ionomer, we see a reduction in charge transfer kinetics for both the systems. It's a lot more for this commercial polyvinyl phosphonic acid than it is for this polytetrafluorostyrene phosphonic acid. So the addition of this binder material is not just enhancing conductivity, it is enhancing reaction kinetics. And then if we look at the gas diffusion, if we in the Nyquist plot, the low frequency regime, and we can calculate the diffusion resistance, which is 1 over the diffusion coefficient to square root of diffusion coefficient, we see the equibion is reducing the diffusion resistance sigma here, and that's because we're promoting diffusivity in the electrode layer. So this binder also affects not just kinetics and conductivity, but gas transport. So this is the conclusion of my talk. This is the decade of hydrogen. It's central to decarbonizing heavy-duty vehicle transport and chemical industry. Delivering hydrogen via the natural gas pipeline is really in its infancy. Most of the work is looking at feasibility of concepts. Does it economically make sense? Material compatibility, embrittlement of the pipeline material, hydrogen leaking through the pipeline. But I think this technology could be an enticing platform for extracting hydrogen when blended with natural gas. I told you a little bit about how these binders, this adhesive in the electrodes is important for the overall cell performance. And not only does it affect conductivity, but charge transfer kinetics and gas transport. And our future work is to actually study this with, purifying hydrogen from when mixed with actual natural gas. So with that, I thank you for your attention. I'm happy to answer any questions.
Any questions here? I've got a couple online. Please.
So my question is about level or an understanding, because you mentioned that the EHP pump can separate and also compress the hydrogen, and how does the compression happen? And if that's quantified, like what is the pressure that's coming out of the pump?
Yeah, so look at this model here is this Nernst equation, which gives us the thermodynamics. This is the standard potential, and then this is the pressure of the cathode over the anode, right? So you cannot compress with not expending energy, right? So when you pressurize the cathode where you're making the hydrogen, you have to expend energy. And then how much you can pressurize is like how durable this membrane is, right? So if you use a reinforced membrane and a thick membrane, you could go, I don't know what I think Banda Barha or somebody, I can't remember who told me, I shouldn't say his name, like 10,000 PSI is possible, okay? But if you think about it, like how you feel hydrogen in a fuel cell vehicle is like 700 bar. So you're not gonna all do it on the hydrogen pump. But, in practicality, you probably do a few bar, tens of bars with the hydrogen pump. We do it at a few bar in our lab, like 3-4 bar there. Not every time, okay? Did I answer your question? Okay. And what was the other question?
Yeah, I was just asking what the outlet pressure would be like on the pump, but I think.
Yeah, so like in the durability test, we put 30 psi in the cathode stream. Okay,
Thank you.
yes.
I was just wondering, so you mentioned like the economical savings from using this method. Are those savings from like reductions in the amounts of like platinum group metals required, or from like manufacturing processes, or like, where is that saving coming
For the hydrogen pump or from the first part of the talk?
from? The first part.
So the first part is just all driven from the materials cost, like just getting as little amount of platinum in the electrode area, right? So you have this high surface area support, they sputter the platinum. It's like a micro pattern support. So like they're tilted, they put it top down, they scrape this off, and then they put these on membranes. Or they'll send it to the people, whatever they scrape off, like they'll put it in an ink, and then somebody will process it further for making electrodes. So in this area of like, sometimes the membrane cost can exceed the cost of the catalyst, like if the production volume is low. But we know that when we go to large production volumes, like 500,000 units a year, platinum is a finite resource, platinum group metals. And so what you ultimately want to do is get the lowest loading possible or just substitute it. But one challenge in that, why can't you just substitute the platinum? There are materials that maybe would give you not comparable, but good conductivity or good kinetics, but they're not corrosion resistant. And that's a key thing. Like that's a very corrosion resistant catalyst, about as good as they come in that regard. Yes.
So then, I guess to follow up on that question a little bit, then the process of manufacturing the black polymers, does it offset the cost of using less platinum enough at scale?
Yeah, good question.
To make it like actually economic?
Not if you buy it from polymer source. So yeah, I mean, I think you don't need a lot of black polymer to begin with. And then like if those monomers, styrene and methyl methacrylate are real cheap, and that polymerization is real cheap. So yeah, compared to the cost of platinum, they would be like pennies on, tenths of a penny on the dollar, I would think. I don't think significant. I mean, now the other processing steps, like doing this like in a fab process, right, where you spin coat, self-assemble, etch, or grow the aluminum oxide etch deposition. That I don't know about the economics of that, but there's some people in our community. We look at semiconductor manufacturing, this miracle of the world, right? We put billions of transistors on a chip, in these large production facilities for all our phones and computers. Like, why can't we adopt those manufacturing procedures for technologies like fuel cells and electrolysis? And that's something I'm interested in.
But then in the semiconductor manufacturing industry, there's also some success rate associated with the production of transistors or microchips. Do you have anything to say about the success rate of the production of these sorts of monolayers or the?
No, we're doing this is like, the frontier, right?
Yeah.
Like, I can say, when I was a postdoc at University of Chicago, this directed self-assembly of black polymer has been done by companies. Our circuits aren't made this way to the best of my knowledge, but like IMET, for example, like they had a pretty large pilot scale fabrication line doing this process. With integrated circuit manufacturing, it's a little different. You need perfection. You can't tolerate the defects. And that's sort of been the Achilles heel for directed self-assembly of black polymers. You have like 300 millimeter diameter wafer, billions of transistors on there, and you can have like 10 defects. We're not looking at how the defects here affect reactivity. They may not matter. I don't know the answer to that question. So we may not need to be as precise or exact in integrated circuit manufacturing for these materials, for this application. But good question.
Got two online here.
Yeah.
Complimenting you in your talk. I was wondering if you measured your electronic conductivity of the binders and how stable are your binders?
Great question. We have not measured the electrical conductivity of the binders, and I think on the stability side, we have the slide up, like the binder was in the system. So we were at 100 hours at 200 degrees C and running, with can't remember, 120 millivolts on the cell. But these are all important things, right? So in the hydrogen pump, the stability concerns might not be as significant, let's say with a fuel cell, because when you do oxygen reduction reaction, you might make hydrogen peroxide or other reactive oxygen species that could degrade the binder. But Los Alamos, some of their papers have looked at cycling stability and they show pretty good stability. But at the end of the day, 100 hours isn't good. You need thousands and thousands of hours. But this is 5 days on a test stand in my lab. Other students have to use this test stand to do their research, right? But that's a great question.
And another one along the line. Also, what method did you use to measure the ECSA of the IDE?
We did not measure the ECSA of IDE. Only for the glassy carbon, like in a conventional electrode setup. That one we did cyclic voltammetry under nitrogen, and we did the hydrogen we calculated the hydrogen under potential from the ECSA to there, because we have a reference electrode. So one drawback of the IDE design is we have no reference electrode, and we do not know the polarization that's coming from the anodic or cathodic reaction. So one thing we are looking at, can we come up with other chip circuit designs where we could get a reference electrode on one of the electrodes, but it won't be interdigitated. Okay, so the interdigitated design in some ways to amplify the signal to noise ratio. We sort of borrowed ideas from other people making thin film conductivity measurements of Nafion, but I think like in looking at the reaction kinetics for one of the reactions, we need a reference electrode there. So if we did the ECSA, it might not be particularly useful in the IDE design.
Okay, another one is on the last slide with the polymer blends.
Yeah.
Do you attribute changes in RCT to differences in ECSA or something else, like structure of the double layer?
That's a fantastic, I want to get an answer to that question. I think this work is not done yet, but we're close to being done, and I will go tell Kartik, let's measure the ECSA. And that might give us some useful information that maybe it's also a surface area effect with the addition of the equivalent binder. So thank you.
Other questions here? Well, thank you so much for being here.
For coming today, and I appreciate the questions, and I'm happy to discuss afterwards too.